So in our previous video, we started talking about how we were going to design the control unit going to be able to start executing our programs. And we started this example looking at the different states the control unit's going to go through and some of the signals that are used by the PC and how they change through those states. So before I start adding more signals to this list, I'd like to show you some of the Vhdl of the control unit so you can get a better understanding of how this is all working. So if we pull up the Vhdl for the control unit, you can see here that the entity is quite long because it's got all these inputs. The inputs are the C and Z, which are coming from the C and Z flag registers, which are coming out of the ALU. The interrupt signal, which is coming from the outside world. The reset signal, which is also coming from the outside world, is an asynchronous overall reset for the machine. And then these are the super important inputs of the control unit. How is the control unit supposed to know what instruction it's supposed to execute to tell the rest of the components what control signals they need to have active? Well, it's going to know based upon the opcode. And what's the opcode? The opcode are those upper 5 bits of every instruction, and for some of the instructions an additional lower 2 bits at the very right end of the least significant bits of the instruction. And as you remember from the RAT assembly manual, that these are the bits that tell you, am I doing a move? Am I doing a branch? They are unique to the individual instruction that you want to execute. Okay, so those are all the inputs. Critical inputs are these two right here. And then you can see all the outputs are grouped based upon the control signals for each module. So here are the control outputs for the program counter unit. Here are the control outputs for the stack pointer unit, which we're not connecting yet, but we're putting them here because you'll need them later. The register file control signals, the ALU control signals, the scratch RAM control signals. Again, we're not using all of them right now, but we're going to use them later, so they're there. The flag control signals, we'll be using the C and Z ones, but not the shadow ones right now. The I flag control signals, again, we're not using those right now, but they're here. The reset control, and then the IO strobe control. Okay, so that is our entity. So it's got lots of different control signals which are going to be sent to all the other components in the machine. And then the architecture is implementing that FSM. So if you remember from CPE233, there's just a sort of a template way of creating an FSM. You first define a state type, and we're going to have 3 different state types: state init, state fetch, and state execute, based upon that state diagram we drew. And we're going to create 2 signals of this type, present state and next state. So these 2 signals are of type state type, so present state can take on any one of these 3 values, and next state can also take on any one of these 3 values. We're also going to create a signal called opcode 7, which is a 7-bit signal, which, as you can see here, is going to concatenate the opcode high 5 with the opcode low 2, which, as we already discussed, are coming in from the inputs, which are coming from the instruction itself. So this SIG opcode 7 is going to become really important because it's going to be the code that tells us which instruction are we trying to execute. Okay, so in our synchronous process, we just say if reset is 1, then the present state becomes the initial state. So if we get an overall asynchronous reset, we're going to go back to the initial state. Otherwise, if we're at the rising edge of the clock, the present state will just become the next state. So that's basically what happens. Present state gets next state. And then the combinatorial process will tell us what is the next state. Okay, so this process is dependent upon the opcode, the current state, the next state, and the carry and 0 flags. First off, what you want to do is just set all the control signals to 0, and luckily this has already been done for you. And this is so that way you only need to worry about setting the ones to 1 when you need to, because because it's in a process, everything's going to happen sequentially. So they'll all be set to 0 first, but then as you move through the process statement, if something needs to be set to 1, it will be set to 1 because it will happen after it got set to 0. Okay, so what are our different present state cases? So case present state is, first case is when the state is the initial state. The initialization state is really easy, so when PS is state init, all that happens is we're going to set the reset signal to 1. So remember there are two different resets. There's the overall input reset, which is, oh, that's a mistake here. This should actually be a RESET, this reset. If reset equals 1, then present state gets state init. And this one down here should be an RST because that's the control signal reset. So if we got to this state based upon the RESET, we need to send a control signal RST to the rest of the components to say reset everything. And after the init state, we go to the next state, which is the fetch state. Okay, so now if the present state is the fetch state, the next state is the execute state, and we're going to increment the PC. That's all you do in the fetch state. You set the next state to execute, and we increment the PC. Because remember, all that's happening in the fetch state is we're getting the next instruction that is at the address pointed to by the program counter. Alright, so you're probably thinking this isn't that interesting. Well, it's everything happens in the execute state. So, in the execute state, the next state is the fetch state, because remember we're doing that diagram of fetch, execute, fetch, execute, fetch, execute. So if we're in the execute state, the next state is the fetch state. And PC inc is 0. We already set it to 0, but I guess this is putting it here again just to remind you that we're not incrementing because we already incremented in the fetch state. And now we're going to use that very important sig opcode 7, which we had defined up here as the upper 5 bits of the instruction concatenated with the lower 2 bits of the instruction. And we're going to use that to determine which which instruction we're using. So this gives you a little template. So if you're doing the branch instruction, you can get these 7 bits from the RAT assembly manual. You look at the upper 5 bits and the lower 2 bits. So when it's this, when the opcode 7 are these bits, that means we're going to do a branch. And what we're going to do then is, in this case, you're going to go ahead and fill out whatever control signals you need to set in order to make that branch happen. Then for the sub case, these would be the 7 bits. Again, you could get those from the RAT assembly manual. And then in this case of the sub, you would set whatever control bits you need to set for the subtract. Then we have this in instruction, this out instruction, and this move instruction. So for this first lab that you're doing, you're just going to fill out the control signals you need for each of these instructions. Now, what's going on here? For reg immediate instructions, only the upper 5 bits matter. The lower 2 bits are not part of the opcode for reg immediate instructions, as you can also see in the RAT assembly manual. And that's why it's showing you it'll take 11001, and then the last 2 bits are basically don't cares. So in order to say that they're don't cares, we just write out all possible options. The lower 2 bits could be 00, or they can be 01, or they can be 10, or they can be 11. So this is just an easy way of saying that the lower 2 bits don't matter. All of them will mean that I'm doing an in reg immediate instruction because all I care about in this case is the upper 5 bits. Similarly for the out and this move reg immediate. Okay, so we finish this case. By the time you're done with the next lab, so this lab you're just going to focus on these 5 instructions, but by the time you're done with the next lab, you're going to have probably about 45 instructions, and then by the time we're done with the entire quarter, it'll be about 48 instructions. So this is where it gets really interesting. So, that's the end. After you're done with the execute state, there's no other states. You end the case for the execute, and then you end the process. And then you end the architecture. So that's what the control unit is going to look like. So let's now think a little bit more about what are the control signals that I need to set. And since our example that we just started used the move instruction, I'm going to go ahead and show you how to fill those out. So for the move instruction, what do we need to have happen? Well, this is a move reg immediate. So we need to think about what are all the control signals that we're going to need to set in order to make the move happen. So let's first look at the PC. We already did a PC increment from the fetch cycle, and we don't need to do an increment in the execute cycle. Do we need to do a load or an OE or a reset or a mux select? The answer to all those questions is no, because a move is a very basic instruction. When you're done with the move, you just need to go on to the next instruction. So none of these PC signals need to be activated. They can all remain 0. So we're done with that. Program has no control signals. Let's look at the register file. What are the control signals for the register file? Well, we have the register write, the register output enable, and we have the register write select. Okay, so we're doing a move. Are we going to have to output, or first of all, are we going to have to write? Yes, we have to write to the register file because we want to move a value from the immediate number into the register file. So we know that RF write is going to be a 1, so let's go ahead and put that in our control signal, control Vhdl file. So I'm in the move reg immediate. I'm going to have to set RF OE equal to 1. So remember, we set everything else to 0, so you don't need to put any zeros in here. Only need to set the 1s. OE, sorry. Not OE, we just talked about register write. Let's go back to there and make sure that's what I wanted to do. Yes, RFWR is a 1. Okay, do we need to read? Now this is kind of a tricky question. Remember that RFOE only controls DX out. So let's look at the instruction. The X column is the left column and the Y column is the right column. Do we need to know what is in R10 in order to move AB into R10? The answer is no. We don't need to know what's in R10 in order to write something over it. We don't need to first read R10. So RFOE is going to be a 0 because we don't need to read anything from R10, which is the X register. Okay, so we have settled that one. Let's look at what else we needed. The write select. Yes, we've already decided we're writing, so we now need to decide what we're writing. Well, remember that move is one of the ALU operations. So the result of the move is going to be coming out of the ALU. And since we want that result to come back, we're going to go ahead and get the result coming from the ALU, which happens to be option 00. So RF write select needs to be 00. I'm just going to go ahead and write that in just to remind us, although we don't need to, so I'll write it as a comment, just so we know we've thought about it. So we already thought about RFOE needed to be 0, and RF write select also needs to be 0. But I can comment these out because remember, we set all of them to 0 in the beginning anyway, so we don't need to write any zeros, but it might help you as you're figuring out what you need to set or not set to make a note that you thought about it. Okay, so we looked at the register file. We're good with that. We figured out what all the control signals needed to be for that. So now let's move on to the ALU. So we're doing a move instruction, which is something that happens in the ALU, so we do need to worry about the ALU signals. The ALU select tells us which ALU operation we're using. And if we look over here in this handy dandy ALU select, we see that the move is 1110. So we can go ahead and put that in our control unit. ALU select is 1110. Okay, took care of that one. Let's see now, ALU op select. ALU op select is allowing us to choose from what's coming out of a register or what's coming out of the program. Now we are doing a move reg immediate right now, not a reg reg. If we were doing a move reg reg, we need to get the value coming out of the register because it's a register value. But if we're doing a register immediate, the number is coming directly from the instruction itself. So we're going to go ahead and grab the instruction value, which has the immediate value, and that's going to be option 1 on ALU op y select. So we'll go ahead and write that in. ALU op y select is going to get 1. Okay, that's good. Let's move on to the carry and 0 flags. So this is now where you need to look at the RAT assembly manual and see if the move is supposed to affect the carry and 0 flags. Since I don't remember, let's go ahead and check that. RAT assembly manual. Here it says, move carry flag not affected, 0 flag not affected. So what that means is we are not going to load the carry or the 0 flag because they're not supposed to be affected. So they're supposed to remain whatever values they are. So if you look at the flag, there's a carry flag set signal, a carry flag clear signal, carry flag load signal. We want all those to be 0. We're not loading it because we don't want to affect the carry. We just want the flag to be itself. So all of them are going to be 0. Same thing with the 0 flag. The flag Z load is going to be 0. All these are 0 because it's not affected. And so again, we don't need to write any zeros, but you can make a note if you'd like. So you thought about it. You can say all flag control signals are 0 because we're not affecting them. And let's see what else. We considered PC, the program, the reg file, ALU, and the flags. That's it. We're not doing the stack pointer or the scratch RAM in this, so we are done. We have figured out what are all the control signals we need to set in order to make this move happen. And this is what you do for every single instruction. You figure out what are the signals that I need to set. So you go through each component and say, what signal do I need to set to make this specific instruction happen? And then you go ahead and you stick it in the control unit itself. Okay, so the next video that I show you will then show you how these control signals, I'm going to add the control signals that we just did to this list and show you how the data is going to move through the computer.